Welcome to EDU World Space.
Hey, all, here's an interesting question that has to do with a spacecraft traveling away from the Earth towards a star. So here you have the Earth. Here is your spacecraft, denoted SC, which has a mass of 36,000 kilograms. And it is traveling at a speed v. You're not given what v is, and that's part of the problem, is to figure out what v must be. And the spacecraft is traveling towards the star that is, as measured from Earth's rest frame, 6.6 light years away. Okay? So what you want to do is you want to find work done by spacecraft such that it reaches the star in so that time we'll call delta T naught. We want it to reach the star in merely 1 year. So this means that you have to find the velocity at which the spacecraft must travel, and this will give you the kinetic energy. And we'll work through that. So the first step, here you have to use equation 26-3a, which is the length contraction formula. And you'll remember that that's given by L equals L naught over gamma. Gamma, as we remember, is 1 over square root of 1 minus v squared over c squared. And so you take the inverse of that, and the square root is on the numerator instead of the denominator here. So first you want to find the velocity of the spacecraft, right? V. And so v is simply the distance traveled, L, over the time taken that these passengers of the spacecraft want to be one year, right? So you have L naught times square root of 1 minus v squared over c squared over delta T naught, right? So v is the only unknown. You know L naught, it's that. You know delta T naught, it's that, right? Okay, let's move to the next page. So what you want to do here is you want to square both sides, and you want to do some clever algebra so that you end up with something like this. 1 over v squared equals to 1 over c squared. It's just from algebra, plus delta T naught, that thing squared, over L naught squared. And so you can rearrange some terms to give you v squared equals c squared L naught squared over L naught squared plus c squared times delta T naught squared. Right. So now we write things down in terms of c and years. So light year is the distance light travels, which it travels at velocity c, in 1 year, right? So we have for L naught 6.6 light years, which is basically 6.6 c times 1 year. Square that whole thing. divided by, again, you have a L naught factor here, which again is C times 1 year. This is a 1, not a L. You square that, and then you have C squared times what delta T naught, remember the passengers of the spacecraft want to reach there in a year. So that's 1 year whole square. So that's great. That means we don't have to convert light years to kilometers, which would be way harder than doing this. And so you work things out here, and what you get is something like 43.56 times c to the 4th times years squared over 44.56 times c squared times years squared. So the years cancel. The c squares mostly cancel. The c squares cancel, sorry, leaving behind a factor of c squared. And so this gives you v squared equals 0.978 c squared. And so your velocity, you take the square root of that, is 0.9887 times the speed of light, which is really, really fast. And so finally, you want to find the work needed to get to that velocity, right? And for this, you will need to use equation 26-5b, which gives you the kinetic energy of a relativistically moving object. And so your work is actually your kinetic energy, which is gamma minus 1 times mc squared, the famous mc squared from Einstein's E equals mc squared, m being the mass of the spacecraft, which is given. So basically all you need to do here is find gamma, and remember gamma is 1 minus v squared over c squared. Right? You have that, and you subtract 1 from that, and you multiply that by mc squared. Remember from here that v squared is 0.978 c squared, so 1 minus v squared over c squared is just 1 minus 0.978. Okay. Take the square root of that, subtract 1, and your mc squared is still outside. And so you get something like 5.74 times your mass, which is 36,000 kilograms, times your speed of light. And we're using SI units, so this will be in meters per second. Speed of light, as we know, is 3 times 10 to the 8 meters per second. Square that. Eventually, you end up with something very close to 1.86 times 10 to the 22 joules. This is a lot of energy. This is actually about 100 times the total energy consumed by the United States in a year. So there you have it.